Okay, I'm back. Looks like the only way you guys are going to get a break from me is if my internet goes out. Um, all right. What I'll do is I'll look at both recordings of this and put them together or something. I don't know. So let me share the screen again. A breather here. See if I can get everything back and pick up mid-sentence. Okay. All right. So what we were saying was that this looked a lot like Cramer's rule. It won't work if the determinant is 0. So you got to have this operator non-zero. So let me set one up, and then I'll look at a 3 by 3, and we'll kind of move on here. So here's what I mean. Suppose we had this linear system of equations here, DE, linear equations. If I rewrite it, now remember I have to bring all the x's over to one side and the y's and leave all of these things, out. Okay, get rid of that. Over there. Okay. I'll move all the x's and the y's over, leave these functions over on the right. Those are my G1 and G2. Okay. I then look at the operators. Well, the operator on this is going to be D minus 3. That's like my L1. The operator on y is just 1, and that's equal to minus 12. If you look at this one, that's just minus 1x. I didn't take a derivative at all of it. It was just the function. And the operator here was D minus 1. Okay? So here's what's going to happen in this one. I form the determinant over here by looking at the coefficients that are here, 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 and here. And on the other side, since what I'm interested in are x's here, I'll decide that first. I will, and you can do x or y first, it doesn't matter. Okay, somebody's waiting to get in. Let's get Haley in. Okay. What I'm gonna do, hi Haley.
Hey, sorry, I don't know what happened.
No problem, no problem. I just got bumped out too, so we're gonna have 2 different videos. You'll see the second half and I'll post the first half. So we're gonna take a determinant here, D minus 3, 1, minus 1, D minus 1. And when we're doing x, we're gonna drop this into that x column right there, and we're gonna leave the y column the same. So that's actually pretty nice, because when I do the y, I'll show you what happens when I do the y. I have the same determinant, but I drop the G1 and G2 into the second column, which is the y column. So G1 and G2, and leave the first column the same. All right, let's see what happens in both of these things. If you looked at, let's see, let's try this one. Just look at this y one since it's on this page right here. If you look at the determinant here, it'll be D minus 3 times D minus 1, cross, and you'll get minus 1 times minus 1. And that's operating on y. If you look at the determinant here, you'll have D minus 3 and 4e to the t, and minus 12 right there. So minus a minus is going to be plus, so it'll be minus 12. Do what I always do when I get to this point. This is just a quick way to get to where you would take it off from the other point. Multiply all this out, and you get your, essentially you get your characteristic equation there. It's m squared minus 4m plus 4, which means the roots are repeated roots of 2. So I know my YC right now really quickly without worrying about the elimination at all. You just had to do that determinant. Now also keep in mind that when you were looking for x, look back here, that determinant is the same. So that can tell you sort of why we were coming out with the same characteristic equation both for x and y and for the homogeneous part of the solution. Okay, so those will be the same. So let me look at the right-hand side, because the right-hand side is behaving a little differently. this actually will get you your function that you got on the right-hand side of this dE. And I'm going to say d minus 3 times 4e to the t, and then minus that thing will be 12. This means to operate on this. So that says take the derivative of 4e to the t, which is just 4e to the t, and then minus 3 times 4e to the t, which is minus 12e to the t, which will end up being minus 8e to the t minus 12. Okay, so here's what you've got so far, at least with the y's. You've got your yc there. You know your function, your general solution is going to look like a yc plus a yp. At this point, there's the non-homogeneous part of this thing. See this, if you look at this thing now, it looks like this: y double prime minus 4y prime plus 4y equal that thing. That comes from that. And you just have to find a yp. Well, you can use, for instance, method of undetermined coefficients. You can make a guess at what this ought to be, then you start plugging back into the equation and matching your coefficients. I did that down here, way down here somewhere. You could finish both of them by finding that yp the same way. Let me show you what x did. If we were doing x, again, this determinant on this side looked exactly the same. So if you look at the homogeneous part, it's going to be C3, C4, e to the 2t, C4t, e to the 2t. All you need to do is change the C3 and C4 because you don't know that they're the same. They're related, don't know they're the same. If you look at the right-hand side, 12 times d minus 12 times d minus 1 minus 4 e to the t. Well, that says, I don't kind of like the order it came out in over here, because really what it says is you want to say d minus 1 operating on minus 12. So guys, what's the derivative of minus 12? Anybody? Derivative of minus 12 is just going to be, it's a constant, it's going to be what? What's it going to be? Derivative of minus 12?
0.
It's going to be 0. And then minus 1 times minus 12 will give you 12. That's where you got that. And then if you cross the other way, you'll see you're minus e to the 4e to the t, sorry, 4e to the t. So you're going to find your yp there by, again, making a guess at this. While we're at it, why don't we make a guess, since we're getting ready to have a test that looks like this. This would have been x double prime minus 4x prime plus 4x equal 12 minus 4e to the t. If you look at this thing, you knew we were going to make a guess at the yp, so I'm going to make an initial guess. Okay, I need a constant there, so I'm just going to call that a. And this looks like 4e to the t, so it's just some other constant times e to the t. That's my initial guess. I look to see if there's any interference with that or duplication with that. Now, I got snared a little bit when I was doing this. I was like, oh no, I've got a duplication in the e to the t, but I don't, guys, because these were e to the 2 t's. Okay, so you don't have to worry about this. Take, if I were going back to the y, I'd be going back to the y right here. But if I now take y p prime, yp double prime, yp prime, plug it all in and match the coefficient. So the point is, at this point, it's the same as you always did. Okay, this is an easy way though to get your homogeneous part with this nice little determinant, and an easy way to get what the function on the right is. It's a little harder with, I think, with having to eliminate every time. Basically, we've done the elimination for ourselves by doing this. Okay, so I did some of this just to check it out and make sure. There's where I made kind of an initial guess on yp. There's no duplication, so it's the one I wanted, that kind of thing. I then made a guess at the same one on the xp, same thing. then I just started grinding it out. And the final solution, you can work it through if you want to check it. I mean, it's right, but if you want to do it yourself, it looks like that. That's what the final solution looks like. Okay. So let me say one other thing. I'm not even gonna. You finish it the same way. You put C3 and C4 in terms of C1 and C2. But let me tell you what happens with 3 variables. Because with 3 variables, this is way easier than trying to eliminate systematically variables. So I'm just going to set it up for you and just do one of them, and you can see sort of what happens. Here's the DE. Notice, or the system. Notice that on the left-hand side, I put all the x, y, z's, y primes, x primes, everything I've got, z primes. You know, you look at that and you're like, it's hard to even tell what you would eliminate. On the right-hand side are my functions, okay? E to the t, 0, and e to the t. So if I want to find out what the equation for x is, I'll pick off the coefficients here. I'll write it in notation for operator notation first. So it's dx plus z equal e to the t. If you put these two together, it's d minus 1x. This is dy, the derivative of y. That's the derivative of z right there. So that takes care of those two. Finally, this one is just 1x and a 2y, and you're operating one time with the derivative of z right there. Here's how I'm going to set it up. Turns out really nice, actually. And by the way, take a look at all 3 of these things. Let's just see what they look like. The left one gives you your characteristic equation. So every one of these things, xc, yc, and zc, are going to be the same. The only thing that's going to differ is your yp, your particular solution. So let's look at how we set it up. We took the coefficients on this thing right here. And it'll be d, there's no y, so d 0, 1 from the first row. And then the second row will be d minus 1, d, and d. That looks sort of like a 0, but it's a d. These two are d's, okay? And the last one is 1, 2, and d. Now, if I want to get x, I replace the x column with this column right here. So drop that right in the x spot, okay? If I want to do y, I'll drop that right in the y spot, leave the other 2 columns the same. When I want to do z, I'll drop it into the 3rd column, right there. Now, all I've got to do, and it is a lot easier than elimination. I don't even know how to describe how much easier this is. Of course, determinants are hard to get once you get 3 by 3 by 3s. But here's what I'm going to do. I'm going to find the determinant of this one. I'll just do one of them for you. I'm going to do the determinant of that one, which, if you remember, we take this d, we delete the row and the column. Let's see if I can get it up here. And when we delete the row and the column there, it's going to be d times, take the determinant of this. I'll write it down here, and then I'll simplify it down there. And I'm doing this one, guys. D times, this will be d squared minus 2d. So I eliminated that row and that column, okay? And the next one is 0. So 0 times the row and column eliminated, just going to give you 0. So that's a nice row to choose there, or to use. On the last one, it'll be plus 1, and you're in a plus position there. You're in an even position. So I'm going to delete that row and that column, and you'll get 2 times d minus 1 minus d. Okay, so all of that right there is what we get from the determinant of that. So we used determinants before to do something else with, but here's another way we can use them. This is where linear algebra and DE are really linked carefully and closely together. So when I did that, I went down here. That's what I got right here. I went down there, I cranked it all out, multiplied everything out, And then what I realize is that I've got this x triple prime minus 2 x double prime plus x prime minus 2x. Look at that. That gives me the characteristic equation. It's a cubic. You might say, oh no, I've got to do synthetic division and rational root theorem. But look carefully. If you pull an m squared out of these two, you've got m minus 2. And if you pull an m minus 2 is there, if you look at that as 1 times m minus 2, I can pull the m minus 2 out, and I'm left with these two. So there are my roots right there. I wind up with a root of 2 and a root of plus or minus I. So xc, yc, and zc, because these are all the same, is going to be c1e to the 2t plus c2 cosine t. Those are all t's. I got a habit of making x's, but those are t's. X, y, and z are functions of t. You got a 0 here, guys, so that's e to the 0 on this one, but that'll just be 1, and you got that. Now, so the thing we're trying to find here, if you look at the right-hand side, one more quick determinant, you got to take the determinant of this thing, which is also not bad, and that'll tell you what the function on the right-hand side is. So I'm going to go ahead, let me go back up to x. I'm going to take the determinant of this to find out what's on the right of that. Get rid of this. Okay. So if I took the determinant of that, it'd be e to the t. Remember, delete the row and column. That'll be d squared minus 2d. That 0 is going to give me nothing there. All right, and then if I take this one, the 1, it'll be plus, it's in a plus position 1 times, delete that row and that column, and that's a 0, and this is a d, d-e to the t, et. Again, I kind of don't, I like the operator in front of the function. It tells me more what I'm going to do with it. All right, and then this is d e to the t. The second derivative of e to the t is just going to be e to the t. Minus 2 times the first derivative of e to the t is another e to the t. The derivative of e to the t here is e to the t. All right. Let's see, hang on, let's see. I did this one, d e to the t. This is e to the t right here. Try again here. That's d e to the t. And if I go down here and look at what I did there, oops, you're going to find out that the e to the t's, oh, there was a minus on the d there. All right, let's see. There's a minus on that d up there. And what it ended up with was that the e to the t's dropped out, and you ended up with minus 2 e to the t. Let's see, let me do that. Let me fix that up there. It was a minus when you switch back. Okay, so if we look at 1, it would have been this times this minus d e to the t, because you're going, if you're looking at that determinant right there, sorry, 0 times d minus 2d. Okay, all right, or minus d. So let me erase that here. It's just going to be a minus. Okay. Okay. So those two drop out right there, and you're left with this. After that, you just have to go back to figuring out this thing by matching coefficients. Notice what I made my guess to be here. It was a constant times e to the t. There was no interference up there, so I'm just going to put all those things in to the original equation, match the coefficients, and when I matched the coefficients, I ended up finding out that what I needed over here for my yp was, or my xp, sorry, my xp was e to the t. Okay. So, so with three equations, it's a lot simpler. All right, if you use determinants. Okay. So that's all I really want to say about. And I'll pull it back. This is mostly just my work, guys. But what I wanted to show you is sort of how the process worked. That's pretty much all I want to say about systems of equations. And I'm going to post a handout that talks about this alternate method that you can look at, as well as the notes. And you'll be able to do that. Again, there will not be any homework due on that until next week. All right, that'll be probably part of our very close to last homework section. All right, questions, anybody? I'm gonna finish up chapter 4 here with section 4.10, which is actually a pretty easy section, but I'm mostly doing it to show you how nice linear equations are. I'm going to talk a little bit about nonlinear equations. They're harder to solve. Let me see if I can find that. Okay. Right there. All right. I'm just going to do a couple of examples here and talk to you about how solving nonlinear DEs is different from solving linear DEs. And then we'll pretty much be through with chapter 4. It turns out that if you, and this is the theory that we've learned, if you've got a linear equation and you have the fundamental set, you have linearly independent pieces, you can write any solution as a linear combination of those things. And any linear combination is a solution. Okay? That turns out not to be true for nonlinear. And I'll show you an example. This is nonlinear, and we're going way back before chapter 4, because you've got a square on this y double prime. That is nonlinear. And you got a square on the y. Nonlinear. I cannot use any of this stuff I've been using for the last 3 weeks on this. You can show that each one of these things is a solution, and you could show that they were all linearly independent. But it's not true for linear that if you take a combination of any of these, you'll also get a solution. This one's easy to see. If you double differentiate e to the x, you'll get e to the x squared, which is e to the 2x. If you raise e to the x to the second power, you'll get e to the 2x. That's certainly a solution. This will also be a solution. Cosine will be a solution. You can kind of see the derivatives bouncing back and forth here and the function, and you end up getting 0 for both of these. However, if you look at this one and you take its derivative and its second derivative, it's a linear combination of the ones that I said were solutions. It's a linear combination there. If this were linear, that should be a solution as well. It's not linear. If I take the derivatives of it and plug it into the DE, remember what the DE was. The DE was y double prime, and then we squared it. And this one was y, and then we squared it. That's what I did. I took the second derivative of this right here, squared it out. All right, there's the second derivative. I put it in. I put in y and squared it out. I did not get 0. It is not a solution. So that's one big difference between linear and nonlinear. You do not have this nice linear combination of solutions as a solution. Okay? That could be 0 at isolated spots where the sign of x is 0, but in general, it's not 0 on intervals, on any interval. Okay. So that's one problem. The second thing is this. We've solved some nonlinear equations. Before we got to chapter 4, we were looking at a lot of different things. We looked at separable, exact, homogeneous. Some of those were nonlinear, but they were very special types. You could separate them. You could tell me it's exact and run through that whole process. You could show me it was homogeneous and run through that whole process. But what happened when we solved those is we got some kind of parameter c in it when we added c, when we integrated or whatever. but it's not, what you got was not a general solution in the sense that every solution could be written in terms of it, okay? So in other words, for the proper C and the combination, you could get a solution. What we found out, and this is sort of going way back, was that we had singular solutions. And singular solutions were solutions that were sort of outside the general look of things. In other words, I might have something with C in it, but I could see something was a solution, but I couldn't find a C that would make it that. So for example, if I look at this one, this was a Bernoulli equation. If you remember, it looked linear, except it had this y squared on the end of it. We actually solved this one, I think. It came out to be y equal 1 over minus x squared plus cx. Now, it's pretty clear that if you look at the dE, y equals 0 is a solution. Okay? I put in y equals 0 here, I get 0, I get 0, 0 squared is 0. It's a solution. But when we solved it, we got that. There is no value of C here that's going to make that 0. If you tried to set it equal to 0 and cross multiplied, you would get 0 equal 1. That's what we called a singular solution. It could not be gotten by any, it could not be gotten by making C something. So we could not get y equals 0 by making C. I mean, the only way a fraction is legally 0 is if the numerator is 0. And that's not going to happen here because the numerator is 1. So you can't get all the solutions out of a nonlinear problem. Now, nonlinear equations are very important, arguably maybe more important in some ways than linear when in really complicated problems. And they're harder to solve, much harder to solve. Sometimes you even have to resort to what we call a numerical solution, which is you plug in all things to the derivative, or I mean to the computer, and the computer looks at slopes of tangent lines in massive numbers and tells you a solution. There are a few substitutions that work. So I'm going to give you 2 substitutions that work, and that'll be all we're going to do with this section. Okay, and there'll be just like a couple of problems on each, and again, that'll be part of an assignment after your test. So it's not going to be on your test. So so let's look at case 1. In case 1, we're going to talk about nonlinear things where the dependent variable y is missing. So in other words, we're going to have a dE that's got in it an x, a y prime, a y double prime, but not a y. Y is the dependent variable. What we've got here is that essentially that y is a function of x. So you've got the independent variable, you got the derivative of the dependent variable and the second derivative, but you don't have y. You don't have y. Okay, it is a function of x. It's actually solved pretty easily. We're going to make, if we see that situation, we're going to let u be y prime. We're going to kind of reduce the order of this thing and see what happens. So if I let u be y prime, and they're both functions of x, then u prime is going to be y double prime, or du dx will be y double prime. I am then going to plug in what I've gotten here. So y double prime, we just said, was u prime. I'm going to have a 2x. And again, y prime was u. So I'm going to put in u right there for y prime. Now, it's easy at this point. When you do this, it becomes separable. It may be not as easy to separate as this one, but it becomes separable. And we know we can solve something that's separable. Good review of separable things. What I'm going to do is say, well, u prime's du dx, and that's 2xu squared. When I separate it, I'm going to get the du over here. And I put the u squared under it. And I'll get the dx over here, and it'll just be 2x dx. That's easy to solve. What we know we're going to do in a separable equation is integrate both sides. So the integral of u to the minus 2 is minus 1 over u, or minus u to the minus 1. The integral of this is x squared plus c. There's my solution. It's done. I will now remake my substitution. Since we knew that u was y prime, I'll put it back in. So minus 1 over y prime is x squared plus c. I'll make it look a little better and invert things there. So we got minus 1 over y prime is x squared plus c. That means y prime is minus 1 over x squared plus c. And the nice thing that you see here is that I cut off my paper. All right, but anyway, you've got something that is separable again. All right, it's separated already for you. So all you have to do now is take the integral of both sides. And you will have y. Okay, I cut it off. Now, guys, that looks like, if you pull the minus out, it looks like an inverse tangent. Okay, and they do something in the book that's you might think is a little fishy, but it makes things nice. You really like to see this thing squared right here. So you could make it a square root of c squared if you wanted to, or you can say, well, I'm just going to replace it with another constant. And that other constant is going to be c1 squared. c1 squared is still a constant. Now it's in the perfect form of x squared plus a squared, which is simply an inverse tangent. That solution is going to look like minus 1 over whatever the thing that was squared here is c1 inverse tangent of x over c1. And then it'll be plus another c, we'll say, call it c2. So that they did this manipulation in the book, guys, and you're like, whoa, what happened there? We just said, well, this is c. I kind of like it to look like something squared, so I'll make it just some other constant c1 squared. And that c1 could actually be, you could see it would be root c, because root c squared would just give you c. But we can do that. That's easy enough. So this one becomes separable. Pretty easy. Questions about that one? The last one I'm going to look at looks like this. We're going to have something that's nonlinear, and the independent variable is missing. In other words, x is missing. These are easy to identify. Your DE is going to have a y, some combination of these things. But anyway, the x is missing. You won't have to have all of them, all right? But x is missing. So here, we'll have y prime, y double prime. If you look at the example that I've got down here, and I'm going to scroll up a little bit. There's the example I'm going to do. Sure enough, the thing that's missing is x. And it's definitely nonlinear. You got a square on this. You got a y times that, where it should be a function of x times that if it's going to be linear. So you've got a problem there. So I'm going to run the same sort of situation as I did before. I'm going to let u be y prime. But now y is a function of u. That's u now is dy dx. So if I look at y double prime, it's going to be u prime. But since u is a function of x, all right, I'll get du dx is that. Y is a function of u, which is then a function of x. That's a chain rule thing. So that du dx is going to be du dy times dy dx. That's because u is a function of y and y is a function of x. So bottom line here, guys, the substitution I'm going to use is this, because dy dx, that y prime was my u. So the substitution I'm going to use is this thing right here. That's a u, not a y. It looks like there's a little tail there, but it's a u, okay? So I'm going to put in y prime is du dy times u. Okay. If I look at this one, then there's y. Y double prime was this one. So I'm going to put in my du dy. All things are, this is a y. Right here. All right, times u is u squared because y prime was u. So I put this thing in right here for y double prime. And I put u in for y prime. Okay. When I put those in, I get y du dy u equal u squared. It's separable. It's only got u's and y's in it. It's really nice. I'm going to leave the du on the left and divide by u squared, which leaves me with 1 over u here. I'm going to put the dy on the right, multiplying through by dy, and put the divide by y, and I get something that's really easy to look at. It's separable. If we integrate both sides, which is what we do when we have separable, du over u will be log u. dy over y will be log y, and I'll put the plus c on that side. I then will just use e here. And if I use e, if I apply e to both sides here, I'll get a u right there. If I do this, note, remember it's u, it'll be e to the log y plus c, but that's just times e to the c there. And I'm going to call e to the c c2, and e log x, e log y is just y. This is a y here. So I get u equals c2y. That's nice. It's also separable again. I'll put the y under here. I'll leave the c2, I'll put the dx over there with the c2. Integrating, I get log y. Separable twice here, guys. That has to do with the fact that you've got y as a function of x and u as a function of y, right? So I get c2, integrate that, integrate this, integrate that, c2x plus c3, apply e again, and I'll have e to the c4, e to the c2x, that one, and then times this, that'll be just times e to the c3, which is just another constant, which I called c4. Okay. I'm going to go ahead and write down the homework here, guys. I will put it on an assignment sheet for you later. But they're only, this is for next week after the test. That page 189. I'll also put a picture of the page and so forth in Moodle when it's time. 1, 3, 5, and 7. And then eventually we'll hand in 4 and 6, just 2 of them. Hand in 4 and 6. One of them is one of the substitutions, and the other one is the other. The other case that you can solve nonlinear ones with is series. Not everybody in here has had series. I'm not going to even touch that, but that is in the section, so we're not going to do that. Okay. Okay, that's all I want to talk about today. Does anybody have any questions about the test, or just in particular? Again, for those of you who came in a little bit late, on Friday we're not going to have class per se. I'm not going to do anything at all Friday, except during that time period I'll have time to actually between. See, I don't have an 11 o'clock on Friday either. So really between, let's just say 9:30 and noon, I'll have some time. If you want to talk to me about a problem or you're having trouble with a particular method, just drop me an email. We'll set up a Zoom and I'll answer your question, and I'll do it all during those couple hours. If I get people waiting, I'll just set up the whole thing where people can click in and come in as you need to. I might be talking to somebody else, but that's okay. You might want to listen. So we'll do that kind of as an office hour. Again, from 9:30 to 12 on Friday, I should have some time. So drop me an email if you want to talk to me, particularly at that time, and then I'll set it up. Questions? Anybody? Okay. Did I just start to hear something? Maybe not. I will have this test posted basically late Friday afternoon. And that's after we've all had a chance to ask whatever questions we needed Friday morning. And then it'll be due by class time on Friday. Is everybody okay? I don't forget to look for that email that I sent that had the sections that were covered. There were some sections in chapter 4 we did not cover. We didn't cover 4.9. We didn't cover 4.6. I don't think we did that. But make sure you look at that email, and if you have any questions, get in touch with me tomorrow or so we can talk on Friday. Okay? All right. Last call. Okay.
I do have a question, but this is not about, it's about the, what's it called, Cauchy-Euler?
Cauchy-Euler equations? Yeah.
Sorry. Okay, so
That's okay. That's okay. You're not German. What?
if I have a, good God, hold on. If I have like a cubic, like a y to the,
Wait a minute. Yeah.
like the third derivative of something,
Uh-huh.
do I have to go through that entire process of
No. Remember what we said when we have, these are Cauchy-Euler equations, guys. Remember we said the form that we thought a sample was going to be something like that. This is what you're talking about, right, Haley?
Yes.
Okay. So if I took 3 derivatives of that, I would, you do have to go to the end of it, but if you look at the first derivative, it would be m x to the m minus 1. The second derivative would be m times m minus 1 x to the m minus 2. And the third derivative, has an m minus 1, an m minus 2, and an x to the m minus 3. It always happens that if you put it in, remember on a Cauchy-Euler, you would have had an x cubed times y triple prime. If you've got that x cubed times all of this, this x cubed is you can factor it out, all right? You do have to crank out by hand the stuff that's left, and I think that's what you're asking me. It's gonna have a bunch of m's in it, okay?
Yeah. I'm gonna go back and plug in like all those derivatives into the original equation.
Yeah. But the nice thing about it is that when you've got an x cubed and on this third derivative, you've got an x to the m minus 3, that's always just going to be an x to the m. And it's going to happen like that in every term of this thing. That's just going to be an x to the m. You then pull your x to the m out, and then you can see that if you pull your x to the m out, you'll have all the stuff that's left is a bunch of m. I don't know, it might have m times m minus 1 plus m squared or something like that. You do have to multiply all that out because that's going to give you a cubic, and that's where you find your characteristic equation.
But for a second derivative, I can just say a equals this, b equals that, and then just put it in.
Yeah, I think I understand what you're saying. Yeah.
Like, okay, so for like our homework, for example, I think the first one was x squared y double prime plus x y prime minus 4y.
Okay.
And a equals 1. And
all right,
b
read it again because this is a good point, guys. Read it again, Haley. Tell me what it was.
X squared y double prime plus 3xy prime minus 4y equals 0.
Okay, now let me tell you something about a second order. We did have a shortcut on second order. And the shortcut on second order looked like this. M squared, the coefficient on the second one, on the second m right here will be b minus a, where that is your b minus, that's your a is 1 here, and your b is 3. Okay, your a is 1 and your b is 3. So b minus a will be just 2m minus 4. You can do that on a second order, okay? We do have a shortcut there. We showed that that was always that. You have to work it out on a one of third order.
Okay.
That's what you're asking me, isn't it?
Yeah, that's exactly what I'm asking.
Okay, all right. We did have a shortcut on that. And if you look back in the videos, after a while I said, okay, let's just use the shortcut. It's just going to be b minus a. Identify b, identify a, and you can use that on your characteristic equation. You don't have to run through it. You don't have any such shortcut on third order. Okay? That makes sense?
Yes.
Okay.
I want to make sure. But even if a fourth order, we still got to go back and work anything out. Only second order is a shortcut.
Yeah. You're not going to get, I'm going to tell you the highest you're going to get is a third order. I'm not going to torture you with a quadratic equation, okay? Cubic's bad enough, okay? So yeah, anything bigger than, we don't have a shortcut for anything bigger than second order.
But what we did today is not on the test.
No, it is not, none of the systems of equations, none of the two things I just showed you about nonlinear things, none of that. This is on chapter 4, having to do with linear equations, linear with constant coefficients, and then these Cauchy-Euler equations.
You might have answered this in the class I wasn't
It's okay.
able to do, but the format of the test, I mean, obviously it's online, but am I going to be able to start it and then go back to it later?
Oh, absolutely. It'll be the same. Yeah. Good question. Once you start it, it's open note, open book. I mean, once you start it, I mean, you still got access to all your notes and all your books. Don't talk to anybody else about it. Don't go to any online sources, but you can, that's the nice thing about this. And I think I probably did say this before you got in, Haley, but you can set it aside. This is mind-numbing work sometimes to do these things because they're messy and they're long sometimes. Do one, step away from it. That means you need to start kind of early. It's not due until Monday. I'm going to post it Friday night or late Friday afternoon. I would probably start it no later than Saturday afternoon and just do a little at a time, walk away from it. Do a little Sunday morning, walk away from it. Do it that way. I think you'll fare better on it that way.
What time do we have to have it turned in on Monday?
My class time would be good. My class time. Yeah, let me just say my class time.
I just know like, I'm going to have some stuff going on this weekend, like with everything going on. So I was going to get it done Friday, but if it's not going to be done till, I'll email you.
Yeah, Haley, we probably need to talk separately because I know you're having some family issues. Yeah, email me and you can ask me whatever questions you've got about that. Okay.
Thanks.
All right, you're welcome. Anybody else?
You can just turn our homework in anytime today, right?
Say that again.
You can just turn our homework in anytime today.
Yeah, that's fine. Anytime today. Some of you have already given me your homework, some of you haven't, but I do need to go ahead and get it out and get it graded because it is part of the test. So I want to make it's the Cauchy-Euler equation stuff. So everybody get it in, and so I can make sure you're doing it right, and then it'll be a pattern for you to use when you look at your test. Okay, so get it in by late this afternoon because I'll be grading it tonight.
Thank you.
You're welcome. Anybody else? Anybody else got a question? Okay, guys, I'll see you on Friday. Drop me an email if you have any questions. We'll set up something on Friday or Thursday, whenever I have a spare slot. Friday's the most obvious one because it's our class time, but we'll take care of any questions then. Okay, I'll see you later. Bye.
Thank you.
Mm-hmm.